Can I still stream? That's the question. All right, so I think we're still streaming with voice this time. And let me turn on screen sharing on Discord's side. Go live. There we go. Okay, so I think we're good. It looks like my voice is fine on the Discord side and also on OBS side. So starting OBS from the command line, somehow this doesn't make I mean it makes the voice part not working. All right. Well, of course it has to be you know it of course it doesn't have to work 100%, because it's the last day of class. Okay, so getting back to resources that you can use during the exam. um, Online GDB is a good resource because it's a web-based interface. So that means even if you have a Chromebook, $200 Chromebook, you can actually use it. The other tools are not quite as friendly to a Chromebook, so you can't really run the simulator inside a Chromebook. The answer is yes and no. You can actually run Logisim with a Chromebook. There is a web-based Logisim out there, but you have to pay in order to save files. So it's not a free service, and that's why I don't have that link up anymore. And on the other hand, it also does not, you cannot run it in CLI mode, the command line interface mode. So so that means, Chromebook it will give you some resources, but not all. But nonetheless, okay, most people should be able to install Logisim and also run the processor, on the computer. So it's the GDB and the C compiler that can be an issue, and this is a great resource for that. So let me switch back to the text window where we have the C code. There we go. So when you look at line 6 to line 18, that's the C program. Okay, that's what the program is supposed to do. And the idea is I give you a faulty implementation. So let's focus on line 20 at this point. The following is a faulty, very faulty implementation of the C code in text toy processor assembly. So I can't even spell my own acronym. Okay, this is supposed to be ASM. Your job is to figure out what is wrong with this implementation and fix it. So there are several things that you want to kind of pay attention to. Is if a line is missing, you want to add that particular line or lines if there are multiple, and comment, and say that that's inserted. Now I have I can tell the differences. Okay, if you do editing in the original document, I can kind of tell the differences, fairly easily. It's not really, convenient, but I can tell it. But it's best if you just kind of use comment. So if this is the line that is inserted, if line 28 is what you have added, then you add the line and then you use the comments, to say it is a line that is inserted. And then you use, after that, you can just kind of comment on why you add that line to the program. If only a part of a line needs to be changed, then you want to add comment after that, and basically just say / changed and then explain why you change it. If you have a line that needs to be removed, you can comment it out, but then you have to use the word removed so I can actually see how you are editing the program. Okay, so that's basically what we are doing with the final. Oh, I need to share with you some other information about the final. Okay, so let me go to the other window and copy a file, or I can just reopen it from here. No, I'll copy it first. fx.ideas to tmp. There we go. Okay, so we'll get back to this program, but before we get back to this program, I want to basically look at this file first. So I think I will make the final time from 9 a.m. tomorrow, which is the 30th, to 9 a.m. on the 31st, because technically the 31st is still a part of the summer session, so it is not not okay for me to use that day as a part of the final. So that gives you guys 24 hours to do the final. I'm not even sure what to call it. It's not exactly an exam. So we'll call it the final project. Okay, so the final project has a duration from 9 a.m. to 9 a.m. So it's basically you have 24 hours to complete the project. Do we have any questions about the timing of the final project? Okay, Catherine is typing. All right, how long do you think it would take? I cannot estimate. Okay, I really is not the best person to ask. Logisim can simulate circuits, but I cannot simulate students. That's a very difficult thing for me to do because I have to basically undo everything that I know about the subject matter and also the experience and all the skills that I have acquired over many years. Um, how many questions? It's just one. That's the whole thing. Okay, there's only one question. I will give you a I'll give you a C program that is implemented in assembly in a faulty way, and what you guys need to do is to fix that program. That's basically it. Um, I do not know whether you need all day or not because that's a very subjective and individual kind of thing. Um, since I'm making the question, definitely it won't take me that long. But based on what the kind of programs that you guys ask me to take a look and help debug, it's not going to take me a whole day, even if I have never seen that program before. So I can't really tell whether it will take all day or not. I hope not. Okay, the idea is I think most people should be able to do it in about at the most maybe 2 to 3 hours. Okay, at the most. But I cannot tell. Okay, so I'm giving you guys the flexibility of 24 hours. This is not a hackathon. So I don't want people to think of this as a hackathon where people have to stay up for 24 hours to work on this. I really don't think that is necessary. But I can't to answer the question. I really cannot. Other than how many questions, there's only one. But about whether you need all day or not, I cannot really answer that question. I don't know for sure. Okay. Um, but that's kind of that's kind of the arrangement is from 9 a.m. to 9 a.m., which is pretty easy to remember, because 9 a.m. is when our usual lecture starts. So we just basically say, okay, from that time on, you got 24 hours to work on it. And there's nothing to turn in per se because I will do exactly the same thing as before. I will pre-share a document for you guys to put your program code in, and then when it's time I will quote unquote unshare the same document. So as far as you're concerned, you just have to find the shared document to basically store your program, to document what you changed in the program and so on, and I'll just be collecting that for grading purposes. Okay, so Catherine has some more questions, I guess. All right, can we cut and paste using your own editor? That is a good question. My inclination is not to do cut and paste, from your own text editor, just because I want to see how the programs change over time. So that is kind of what you're using Sublime and then dump into the assembler. I'm assuming Sublime is an editor in Mac OS X. Okay. Well, you can use Google Document to do that too. I'm assuming that Sublime has some features that Google Document does not have. That makes it kind of significant and easier to use. Oh, okay, colors. Okay, gotcha. Um, hmm. That is a very good question because I want to see how programs change over time. I don't want to just see the last revision of a program. So if I can see how a program changes over time, and explanations of those changes, I'm okay with that. So let me think about this a little bit, okay? Because I might let people just use a GitHub to do that. So that way you can use Sublime to edit the text, but then you use GitHub or some other tool for revision controls that you can just upload the code and then it maintains the difference between versions. So that way I can still tell, how the program changes over time. Because the one thing that I do not want is someone to paste in the corrected program in one single shot right before 9 a.m. on Friday and call it done. So that is one thing that I do not want, and I want to make it very explicit that people cannot or should not do it. If I see something like that, I won't grade it. Yeah. So Google Doc is one place you can do it. If you really want the color coding, let me think about how we can do something like that. So that's going to be something I have to kind of work on like right after lecture today. So I'll give you an answer for sure, maybe at about noon time today. All right. So I'm hoping that issue is okay. All right. Cool. Okay, I see. It's got line numbers. So I'll think about alternatives that will still meet what I need for submissions, but it will make it more flexible for you guys to use editors of your choice. All right, so getting back to the exam, things that we can count on, things that you basically say, okay, these things are always going to be held with, these rules are always going to be withheld, are the caller-callee agreements. The caller-callee agreement, basically says, the callee, the subroutine being called, can change registers A, B, or C, and the caller cannot make assumptions, cannot say, well, I know this subroutine does not change register A. I know this subroutine does not change register B. No such assumptions can be made. Okay. I suppose. I mean, you can link a Google Sheet to a Google Doc, or you can share your Google Sheet with me. Okay, so that's the other thing you can do is you can share whatever cloud-based document with me, as long as that cloud-based document has revision tracking, and Google Sheet definitely has tracking in it. So you can just share it. Martin, you can share your Google Sheet with me at the beginning of the whole day. And the idea is I just want to see how a program evolves or changes over time. I don't want to just see the final version of it. All right. So getting on to the agreement between the caller and the callee. The callee is to return a scalar value using register A. The caller is responsible to push the arguments. The last argument is pushed first. Yeah, you're welcome, Martin. And then the caller has to push the return address last, okay, before jumping into the subroutine. And then the callee is responsible to allocate for any local variable that it is using, because the caller has no idea of the local variables used by a callee. The callee is also responsible to deallocate the local variables. It kind of makes sense because the caller has no idea how many bytes on the stack the callee is using. Now this part is a little bit out of the ordinary because we know that the caller is responsible to push the return address, but it is the callee who is responsible to retrieve and deallocate the return address. The stack pointer should remain balanced, which means the stack pointer value should remain the same before and after calling a subroutine, after the arguments are adjusted. Items below the stack pointer are subject to change without the program realizing it. This is because of interrupts that we really haven't talked about, but this is one thing that I want to make very clear is do not assume the content in RAM that is below where the stack pointer points to will maintain their values. In other words, they can change without you knowing it. Okay, so you have to make that assumption. Location FF in RAM is the location of the stack. Basically, it is quote unquote, it's called the bottom of the stack because when we grow a stack in a normal sense, the top of the stack is the last item. But in memory locations, the top of the stack is actually the one that has the lowest address in memory. So it's kind of reverse in that sense. The stack can grow as low as the last byte used by the program in RAM, because if it runs over when they start to overlap, then you are having your stack to corrupt the program that is also living in RAM. So these are the things that you can count on. You basically have to play by all of these rules when you translate the C code into assembly code. So the requirements is that the assembly code needs to reflect the logic of the C code, so it cannot be something that is just equivalent. If I give you a recursive version of a subroutine, and you say, well, but I can do this without recursion, I'll just rewrite the entire code in a non-recursive way, that would not count. Okay, so you have to follow the logic of the C code. No rewrite of the code unless it is necessary. So if somebody says, I don't recognize what this chunk of code is really doing, but I know what it really needs to get done in the C code, so I'm just going to remove this entire chunk of code and rewrite it the way that I want it, that does not count either. Sections of the code can be missing, so if you recognize that a chunk of code is missing, you just put it back in and use the comment to let me know that, okay, this chunk of code was missing and it is here now. The errors that I introduce into the code can include syntax errors, which are the easy ones to fix because you can just run it through the assembler and then the assembler will catch most, if not all, of those syntax errors. But there will also definitely be logical errors. The logical errors are more difficult to catch. So we'll talk about the logical errors for the most part, in today's lecture. The resources that you can use, or I think you probably want to use these resources. The first one is the opcode table, your spreadsheet, or your Google Sheet. The idea is it is here, okay? It is available, but I think most people should not be needing it by now, okay? Because we have been doing enough programming and enough sample code that the opcode table really should not be needed, but it is available, okay? Just about any online resources you can use. The assembler is particularly useful as well because even if you don't want to run the program, just putting the program into the assembler will help catch certain problems. Like if you define the label twice, it will find it. If you refer to a label that is never defined anywhere in the program, it will find that problem. So the assembler is good for catching certain things and it's certainly not difficult to use. The trace analyzer, on the other hand, is a little bit more difficult to use. Someone just kind of informed me yesterday that that person did not know how to run Logisim on the command line in Windows. But that's a topic that I have already talked about, I think in week 1 or week 2, because I mentioned a test circuitry, so that people can test the circuit, using the command line and just look at the trace, look at the output. So that was already discussed at the very beginning of the summer session. So I don't know what to do because I use the CLI mode of Logisim, like in every single lecture. So I do know that I'm using Linux and most people do not use Linux and they use Windows. But the command line is very similar whether you're using Linux or not. The only difference is how you specify where to find a file, which is not a topic in assembly language programming. That is about how you use Windows, how you use Linux, how you use Mac OS X, or whatever operating system that you're using. So it is not really an assembly language programming topic. If you put all the files within the same folder and run Logisim within that folder, you don't even have to worry about how to specify the path to a file. Okay, so based on that assumption, I would say the trace analyzer is a very good resource to use because it captures how a program runs. Okay, now when you look at the result or the analysis tab of the trace analyzer, you kind of have to know ahead of time what you think the program should do because what you're doing with the trace analyzer is to look for discrepancy. You're looking for things where, hey, by this time I think this should have happened, and then instead the trace analyzer may say, well, not exactly. Okay, something else happened. Okay, I'm supposed to be executing over here, or the conditional branch should have happened, but it did not happen. So the trace analyzer is helpful because now you can trace your way back and say, why did that conditional branch not happen? Why is that flag is clear? Why is it cleared when I think it should have been set? Okay, so you can go back and track down problems during the execution of the program, but it still needs you to know what you should be expecting, so that you can look for the differences, and then you can find the bugs, and then hopefully once you find where the discrepancy is, then you can go ahead and fix it. Obviously, Logisim is a good resource to use. Okay, that kind of goes without saying, but it is available. All the class notes, okay, everything on Canvas, everything that is on Discord prior to the final project, you can use. Okay, I will probably open a new text channel for the final project, so I can just kind of group all the discussions, all the announcements, that is specific to the final project in that text channel, just so that you don't have to search through a whole bunch of other stuff to find announcements. Past programs that I have done, things that have uploaded through Discord or through Canvas, you can certainly use those. You can use YouTube, all the recording of past lectures you can watch too. It is probably not a good idea to rely on my lecture recordings, in the final project, during that one day, but it is available. So any resources that is already available before the final starts, can be used. Do nots. Okay, so there are very few. Okay, but there are some do nots. So the first one is use any means to, in quotes, attempt to show a possession of a level of competency, knowledge, or skill beyond the actual level of that person, okay, the person who is turning in the test, or another person. Okay, so this refers to collaboration. Okay, let's just say that I'm the person. Okay, so let's say that I'm the person and go like, well, I don't think I understand this concept, or I don't think I know how to do this, but I know so and so has a much better grasp of this concept. I'm just going to ask that person about how to solve this, okay, or where I should go from here. Okay, that is not allowed in the final assessment, because the final assessment is supposed to be right here, individual. Okay, so the submissions should be individually, originally, and independently derived. So individually means not relying on somebody else. Originally means well, I mean, original versus not original, copy from somebody else. Okay, borrowed in quotes from somebody else. Independent, okay, means it is not dependent on somebody else. Okay, it is not an answer after consulting with somebody else. So during the final assessment, do not consult another person. You can consult static resources, okay, as long as it is not an interactive resource or it is not specific to the exam, it is okay. So that includes, do not share documents during the exam. Okay, don't share documents with somebody else. Don't talk to another person in the class during the final assessment. Okay. Any evidence suggesting otherwise will be assessed very carefully. I am fairly good at spotting those things. Okay, I'm not saying that I would catch every single one, but I'm pretty good at it. And if I think the situation warrants it, incidents will be reported to the student conduct officer. And that would not be a very good thing to happen to most people. So I'm just telling you guys ahead of time, okay, what I'm expecting, in the final assessment. So do we have any questions about this document for now, before we get back to the actual sample exam from last semester, I should say? Okay, no questions. All right, so let's go back to the sample question. Okay, and there's also a solution. Okay, this is really cool. Let me show you this. Oh, nope. Let me go. Right, there we go. Okay, so let me show you this. It depends on what kind of editor you have. With NVim, new Vim, and just about any Vim, I think will be able to do this. Is you can display it side by side with diffs. Okay, differences shown. The original question is on the left hand side, and then the solution, quote unquote solution, is on the right hand side. So this shows you what lines you need to change, where the problems are, and what the problems are. So the solution really doesn't give you the actual correction, but it will tell you what is wrong or what needs to be changed on certain lines. So that's how you can use the solution to help understand, what is wrong with the program. So given that is a tool, okay, you can use any tool to look at the diff between the two text files and show it like this. So let's go ahead and just focus on the sample itself, so that we can manually go through the whole thing, well, possibly the whole thing, and find out what's wrong with that program. So we'll do it like this first. But I'm going to extract the C code so I can display the C code on the side. So this way we can compare the C code to the assembly code when we try to spot problems. So this is line 6, and this is 6 to 18. We want to write it to a new file. We'll call it sample.c. Okay. And the first thing we want to do is to look at sample.c and fix all the comments. Oops. Almost got it. Not quite. There we go. Nope. One more time. Replace all the begin line / with nothing globally. There we go. Okay. So this code actually compiles in C. And you can see that it's not really that difficult of a program. And this is supposed to be just one question out of 3 of exam 2 in the spring semester. But it serves as a good example of what your final exam may look like in terms of the format, not in terms of the complexity. So if you look at main, it has got a local variable. It is an 8-bit signed integer. It is initialized to 8 first. And then we have a function call, to f. Basically, it's a nested function call. It's not recursive. It is not recursive because the function itself does not call itself. Okay, function f does not call function f. So we are using the return value of calling function f to serve as the second parameter to calling function f the second time. So it's nested, but it's not recursive. So you can kind of imagine what needs to happen here is we need to first calculate what is x minus 2, push it on the stack, push 2 on the stack, call f. Okay, when f returns, push that on the stack 2, and then push x on the stack, and then call f one more time, and then whatever the second invocation of f is returning, store that into local variable x, and we're done. Okay, so now we look at function f. Okay, function f is pretty simple. The first thing we need to do is to compute, what is 2 times fx, and in this case, multiplication is not implemented in text processor, but you can always add a register to itself to double it. Okay, so doubling is easy to do, and then we subtract whatever f of y has, from the product of 2 and fx, and whatever this entire expression is the value that we are returning. So this one does not have any control structure. There are no conditional statements, no ternary expressions, no loops. It's fairly easy. Okay, yours is not going to be as simple as this. Okay, because remember, this is question number 1 of exam 2, where students only got 80 minutes for the entire exam. You guys got about, I'm assuming that you have 2 hours to work on it. I'm not going to assume that you guys would work on it, 24 hours. All right, so this is, the original C program. So what we want to do now is to look at the C program and also the assembly program at the same time, and we'll start to, fix, potential issues. There we go. So it is now side by side. I'll turn on line numbers so that this way I can, there we go. So we can actually look at, the individual lines. All right, so we'll get past all the comments explaining, the program, and this is the actual beginning. So you can see how I used comments here to indicate this is the beginning of the faulty assembly code. And using NeoVim is really nice. I wouldn't call it a cheat because you can't use any editor that you want to use, at least to view it. Okay, so that's one thing that you can also do, is to use a particular editor to view it. And then, but when you want to make changes, you want to make the changes into Google Doc directly. So that's one way to do it. It is kind of cumbersome. So I will try to find a different way so that people can use their favorite editors and still be able for me to look at how a program progresses over time, because that's what I want to see, is how it changes over time. All right, so right here, CLR clear register D is in red because there's no such instruction. So Sakio said, wait, so are we copy and pasting into Google Doc and then editing over there? Actually, I will give you the Google Doc with the assembly code already embedded into it. So all you have to do is to just, keep editing it. So what you do is you edit the Google Doc content, copy and paste that into the assembler if you want to assemble and run it. Some people can just do it statically without ever using the assembler. Highly not so recommended, but some people can do it. But as I mentioned to Catherine, I also want to consider a way so that people can use their own favorite editors. But the idea is I want to see how a program changes over time, and that is going to be the difficult part. I have to think of a mechanism to do it. Okay, thank you, Catherine. But you may not be the only person who wants to use a different editor, so I will think about it, and come back with potentially a solution and answer to it. So I'll give it a chance. Okay, I'll give it a try and see if it works. Okay, so getting back to the program. So this does not work, but we can always use, subtract D from D, to put a 0 into register D, so it accomplishes the same thing. So according to the document earlier, I have to say changed. Okay, clear does not exist. Okay, it does not exist. Sub DD initializes register D to 0. Okay. So this way, I'm documenting what I am doing to the original source code. So here's the beginning of function f, and we want to define the labels as offset from where the stack pointer points to. This is highlighted in red, which is a pretty good indication that it is a syntax problem. Now, if you put this program into the assembler would probably choke on this line as well. It is missing a JMPI instruction to main. Very good. Okay, so we need a JMPI to main, and this is inserted. Okay, need to skip the definition of f. Okay, very good. Good job, Richard. And over here, we have a few problems, because return address is supposed to be 0, but we don't use a equal to do it. We use a colon to do it. So changed. Okay, colon should be used instead of equal to. Okay. F of y is return address 1 plus. That doesn't look good to me. Okay. In fact, this is going to be a problem because you can see how actually this one is not that big of a problem because f of y is the second argument or second parameter. It is supposed to be on top of f of x. So if you just change these two, one is, just change the definition of x and y, then it'll be okay. So we say changed f of x is has a lower address than f of y, and this is also changed. See above, okay, because it's really the same change. All right, so now we got the correct offsets. The next thing we do is we look at LDIC, fx1 plus, and that's for doubling. Okay, okay, so you want to keep track of what register C has. So register C actually has an offset to f of y, fy, because fy is the same thing as fx1 plus. So we don't know whether it is okay or not. So at this point, I cannot fix it or not fix it. The next line is obviously wrong because it is in red, which means it is a syntax problem because load requires parentheses in the second one. Okay, so we'll say parens go to the second operand. Okay, but this is not going to work because this is just an offset. Register C only has an offset, which is not an address of anything in memory. So we really should not be dereferencing it on line 60. So that means, if we are intending to use register C as an address of something, and it only contains an offset before, that means we are missing an add CD instruction here. Okay, this is added or inserted. So registered C is the address of something. Now the question is, what is that something? It depends on how we intend to use it. Okay, so now we know what register C has, and then later on we have gotten this portion here. Register C should now have the value of f of x. All right, so the command is now reminding us that by this time, by line 62, register C should have the value of f of x. But we know, based on this code, it does not. So that means, we have to now change line 59, remove the 1 plus, so that register C is now the offset to f of x and not f of y. So by the time we get to the comment on line 62, register C will then really have the value of fx. So are we doing okay with this, with all of these corrections at this point? Okay. Well, once we are done with this, we'll compare to the solution and see whether I caught everything. We can actually run this code and see if we caught everything too. All right, so here's a line 62, excuse me, line 64. Line 64 is copying register D to register B, and then we increment it twice. So in your case, okay, you might want to track it, okay? So you can now say that B is the same as the stack pointer, and then whatever is at the stack pointer is the address of the return address. So, and then if you add 1 to it, it becomes the address of the first parameter. If you add it one more time, it becomes the address of the second parameter. Okay, so now if I do an indirect read, then B becomes the value of the second parameter, and then I perform a subtraction, so that B is fy minus whatever register C has, which is fx. And you can see that there are a few problems here, but before we get to that problem, okay, we want to see how the program ends. And you can see the program doesn't end very well, okay, so because we have a red line here. We are loading D into C. It's in red because syntactically it is not correct. So now the question is, what is it supposed to be? Well, this is the return code, okay, so we are supposed to be returning at this point. So that means we need to use the stack pointer to point to the return address put the return address into register C, deallocate the return address, and then do a JMP-C in this case to return back to the caller. Okay, so we'll say this is changed, need parens for the second operand, and this one is fine, increment D is fine, but this one is inserted to actually branch and return to the caller. All right, but the code, even though now I have fixed most of the problems, is not entirely fixed, because what I have computed is fy minus fx, but the code in the C implementation is supposed to be 2 of fx minus f of y. So I got to make a few adjustments. The first thing is, how do we find 2 of fx? So now we need to go back to when we first compute fx. Okay, so there we go. So on line 61, register C would have the value of fx. So what we need to do is to add cc, so that register C is now, okay, this is inserted, C is now 2 times fx. After we compute y, the direction of the subtraction needs to be opposite. Okay, so we need to fix this line here. So we need to say this is sub CB, and then we say changed. Was it in there originally? Yep, it was in there originally. So we have to change it so that we are so that C equals to f2 times fx minus fy. There we go. And then we also need to have one more instruction here, which is CPR-AC. This is inserted. Return value needs to be in register A. So that's kind of what I'm expecting to see when I grade this particular submission, is to look at all the things that are changed, things that are deleted, things that are inserted, and also the rationale, the reasoning behind it. Okay. Now, if I was doing this entirely in Google document, then all the editing would have a log, kind of a trail of the change in time, so I can actually go into the history, or the history of the revision history of a document in Google Doc, and find out what was changed when, and what is the reason why it got changed. Okay, so that is something that I want to be able to see. So are we okay so far in terms of what I have worked on in this code at this point, or do we have any questions at this point? Okay, looks like we are still good. All right, so we are moving on to main. So here's main, and main has a return address. No, main does not have a return address. So what we want to do is to say this needs to be deleted. Okay, main does not have a return address because nobody is calling it. So that means main x needs to be changed to 0 because that's the only thing in the frame of main. Okay, so this is changed. Local variable x is where the stack pointer points to. Increment D, really, I mean, incrementing D is a deallocation of something on the stack. Right off the bat, are we deallocating something from the stack? There's nothing on the stack right now. So this really is supposed to be a decrement D. Okay, so changed decrement D to reserve a byte for local variable x of main. Then we call f the first time. So when we call f the first time, we are talking about this particular call. So we are looking at excuse me, I forgot about the initialization. So we have to do the initialization first. So we load register A with 8, which is what we want, and then we put it into whatever the stack pointer is pointing to. This is actually okay, because the stack pointer really is pointing to local variable x at this point. So if you want to leave comments only for yourself, that's fine too. You can say this is okay as long as you're not using these words, changed or deleted or inserted. I will ignore that. I would just say that okay, that's your own comment, it is okay, not a problem for me. Now we move on to the second line, which is loading the offset into register C, and then we store it right away. We store C to where the stack point is pointing to. That seems awfully wrong to me, because main x is actually just 0, so we are storing a 0 to where the stack pointer is pointing to. That's really just kind of wrong. So now the question is, what are we supposed to do here? We need to call f the first time, which is the inner call. Alright, so let's see if we can identify something else. So if you look into the context of this program, there are two function calls. One function call is here, and one function call is over here. So we are handling the first function call, which is supposed to pass x minus 2 as the second argument. So that means loading the offset into register C is a good first step to do, but we are not ready to store register C on the stack just yet. So there are a few things we need to do in between. The first one is an add CD. So this is inserted. So the C is now the address of local variable x of main. But that is also not what we want to push on the stack, because we need to first we need to get to the value of x. So that means we need an indirect access like this. So the C is now the value of main x. But even that is not good enough, because we have to subtract 2 first. So we have to subtract 2, which is decrement D. Decrement D is fine. If you want to load 2 into register B and then subtract register B from register C, that works too. So I'm just using these two. So this is also inserted. This is inserted. C is now main x minus 1. This is also inserted. C is now main x minus 2, which is what we want as the second argument when we call f the first time. Okay, so Bopinda said, I think we're missing to compute the address after line 78. Nope, we're good. The stack pointer points to the local variable x at that point, because local variable x is exactly where the stack pointer is pointing to at that point. Yep. Alright, so line 85. So once we have that, we need to push it, but this is not ready yet, because we have to decrement D to allocate a byte on the stack. So this is inserted to allocate byte for argument 2. This is argument 2 of calling f the first time. So this one is fine. So I'm just using the regular command and say that this is just for pushing x minus 2 on the stack to handle this portion of the C code. Then we want to push 2 on the stack. Load 2 into B, decrement D, store B into where the stack pointer points to. Looks good to me. So this is pushing 2 on the stack. We decrement D, we load B with .5 plus, and then we store B to where the stack pointer points to. Well, that looks good to me. We're pushing the return address on the stack. And then we continue execution at the subroutine. That's good. When we come back, then we have to ask, is that okay? Are we going to push the return value of the nested call to f right away? Because when you look at these two lines between line 94 and line 95, that's really pushing the return value on the stack. Yes, we still have to deallocate the argument first, and there are 2 of them. So we really need to increment D twice. So this is inserted, and increment D again. This is also inserted. So the first one is to deallocate argument 1 from the stack. The other one is to deallocate argument 2 from the stack. So now at this point, okay, right between line 95 and line 97, right here at this point, the stack is now quote unquote balanced again. Okay, because we push 2 things on the stack. Actually, we push 3 things on the stack, but one is already popped, or it's already deallocated by the subroutine itself. So we got 2 more things on the stack, meaning those arguments, and now they're deallocated. So at this time, the stack is quote unquote balanced. So it is time now to push the return value on the stack. So if I want to remind myself what this is doing, this is pushing f of 2x minus 2 on the stack because we need it back at some point. And then after that, we have to push x again on the stack. So we load the offset into register A, and then we decrement D, and then we push A right away on the stack. That doesn't look right to me. Okay, there are a few things wrong with this. The first one is this is not how we get to x anymore, because we got that one extra thing that is sitting on the stack. So that means we have to compensate for it. Okay, so this line is changed. Offset to x is changed because we just pushed f of 2x minus 2 on the stack. So it's off by 1 byte at this point. And then we need to do the add AD. Okay, this is inserted. Okay, so that a register A is now the address of main X. And then after that, we still need an LD instruction. So we need LDAA because we are not supposed to push the address of X on the stack. We're supposed to push the value of X on the stack. So this is also inserted. A is now the value of main X. Then we can go ahead and decrement the stack pointer to allocate for that byte, and then we actually store register A, which is main X, to where the stack pointer is pointing to. Alright, so David is asking, shouldn't the decrement D be after you push? So the push is over here, and I can put this decrement D here. In fact, we want to put it over here instead of earlier. Lines 97 to 98. You mean to swap the order of lines 97 and 98, David? No, you don't want to switch the order, because if you switch the order, then you are changing something. Then you're okay. If you reverse the order, okay, if you reverse the order of line 97 and 98, then the store instruction would actually have stored the return value of f of 2 and x minus 2 to local variable x directly. It is not pushing it on the stack. So the order is actually correct between line 97 and line 98. Okay, so if we want to see what is on the stack at this point, okay, so if we want to see what is on the stack right after the 2 increment D, this is what the stack looks like. The stack has the stack pointer pointing to local variable x of main, and that's the only thing on the stack right now at this point. And then after this, we have main x on the stack, but the stack pointer is pointing to something that is uninitialized. And then after this point, we have main x on the stack, but then the stack pointer will now point to the return value of f of 2x minus 2 because we just push it on the stack. So it's a good idea to kind of keep track of what is supposed to be on the stack at every single instruction in the program. So this way, when you look at the trace, if the program doesn't work and you look at the trace, then you'll be able to figure out why it is not working. Alright, so we are resuming the changing of the program. So we got a decrement D over here to push, and register A does have the value of main X at this point. So between lines 105 and 106, it is really going to push main X on the stack, so that's good. and then we are supposed to push the return address on the stack, and you can see how this is a .6 plus. It is, let's check whether it's right or not. Okay, just because we usually use .5 plus and this is a .6 plus doesn't mean it is wrong, because it depends on what is between the LDI instruction and the JMPI instruction. So we want to check that first. Alright, so this is a .6 plus. The LDI instruction would use up offset 0 and 1. This is going to use up offset 2. This is going to use up offset 3 and 4. So this is at offset 5. So the .6 plus is indeed incorrect. So we need to change the 6 back to 5. So this is changed. The return address is 5 bytes from the LDI instruction instead of 6. And then we store it to where the stack pointer points to. The stack pointer is already adjusted prior to the LDI. We continue execution in the function f. So that looks good so far. But after we return from a subroutine, the caller is always responsible to deallocate the arguments. So we need to increment d in this case, increment d and increment d. This is inserted to deallocate argument 1 from the stack. This is inserted to deallocate argument 2 from the stack. So at this point, between lines 112 and line 114, the stack should be balanced at this point. Okay, so we can say stack should be balanced again, which means the stack pointer should now be pointing back to just the local variable of x. Okay. All right. So in the C code, we got one little thing to do, because once we have the return value of the right hand side, we need to store that to local variable x. And the attempt to do that is here. It looks like we try to load the offset of main x into register C, and this is highlighted in red because LD cannot take it like this. LDI, on the other hand, can take it like this. So we change it. Okay, so that C is now the offset to main x. But if we just have the offset, we have to compute the address. So that means we need to add CD. This is inserted. So the C is now the address of main x. And once we have the address of main x in register C, we don't want to load because we want to change it. So we want to store instead. So we want to change this to a store instruction. Okay, so you have a choice here. You can either delete it and say that we don't need to change register A and then insert another line, or you can just go ahead and change it. So either way is fine. So we are replacing it like this. So this is changed. Store to main x instead of reading from main x. And then we have a halt instruction at the very end. Aha, we are missing still one little thing. We have to do an increment d, which is inserted to the allocate x from the stack. All right, so that should do it. Okay, so I have done everything that I can do within a reasonable amount of time just looking at the text. So I'm analyzing the program and trying to figure out things statically. But this is not gonna fix everything. Okay, I probably missed a few things. Okay, I cannot tell, but I probably missed a few things. So now it's time to actually run this code through the logic analyzer. Well, run it through the CLI mode of LogicSim, collect trace, and then look at the trace analyzer. Okay, so we'll go ahead and do that. I'm just looking at the time. Okay, so we're good here. All right, so we'll go ahead and do this. And switch to our assembler. And where's my assembler? Okay, so over here. All right, So you want to keep your assembler, basically before the final, you want to line up all your resources so that you don't have to find the resources, using the time in the final. So in fact, you might want to prepare, all the things today before you sleep tonight. So this way, you know that you got everything prepared, and so tomorrow you won't have to, kind of find all your resources, using the time for the final to find all your resources. All right, so we want to look at the RAM file just to see whether there are errors. Okay, so it looks good. And it doesn't hurt to kind of scan through all this stuff here to make sure that everything, looks okay. Okay, so it looks okay to me. So now we say file, download CSV, and we save the file as sample.csv. Okay, so now you have a choice, okay, to quote unquote debug the program using the simulator. You actually got a choice. One thing you can do, okay, which is not something that I highly recommend, but you can do it this way, is to use the GUI mode of LogicSim. So you reset the whole thing first, do a Control R, go to RAM, go to load image, and then load it with the file that that was just downloaded, sample.csv in the temp folder, and you can run the program from here. Okay, that's okay, but you kind of have to know what you should expect as the final state of the processor, because you can't really easily look at the intermediate process of running the program. So for those people who absolutely do not want to learn how to run LogicSim on the command line, this is doable, just not recommended. All right, so Catherine is commenting. So the way you worked the code in NeoVim is what we shouldn't do. We should work on it in Google Docs. That is correct. But I do it in NeoVim because I want to display the C code on the side, and that's an easy way for me to display both the C code and the assembly code. Oh yeah, sure, no problem. Yep. Yeah, Google Doc has most of the editing features. It just doesn't show line numbers and stuff like that. And as I said, I'm going to look into a different, possibly a different mechanism, so we can still allow people to do it using a different editor. Okay, so let's check this out. Okay, so I'll just go ahead and run this program. Okay, I'll be brave. Okay, because I typically don't like to do it this way. I would turn the tick frequency to maximum, and then do a Control K to let the program run. And it has concluded. Okay, I know the program is done because the halt pin should be a 1. Yep, there we go. The halt pin is a 1. I type Control K again. So now I have to look at this program and go like, well, how do we know the program worked or not? There are a few things you can check. You can go to the register bank, right click on it, look at register D. Register D is back to 0, 0. So that's a good sign because it tells me that the stack is balanced. Okay, that's good. Then we look into RAM. Okay, so we look at RAM by using edit content on RAM. And we look at the last location. It is 1, 2 in hexadecimal, which is 16 plus 2, which is 18. So the question is, am I supposed to get 18 back? Okay, so we go back to look at the program in C again. Okay, so if you track down this program in C, this the first time we call F, this is going to be a 6, this is going to be a 2. So we have 2 times 2, which is 4, minus 6. That's a negative 2. So that means this portion here is a negative 2. And then we have 8, which is still in X, minus, wait, hold on a second here. I just, no, I think that's correct. That's an 8, and this is negative 2. So when we get in here, we have 2 times 8 minus negative 2. So that means we're adding 2. So that means we have 16 plus 2. So having 18 stored back into X, seems to be correct to me. Okay, so I think I fixed everything in the program. Okay, but there's another way to check this program because I don't trust myself at all. Okay, I look at this code. This is very obscure. Okay, my mind cannot track the details like this kind. Okay, so I might have made mistakes already. So what I do is I compile the C program. Okay, because remember the C program is supposed to be compilable. So we compile with the debug option using, oh, better yet. Okay, let me show you something that's even better. So we cat sample.c to xclip cell clip. So all this does is to put it into the clipboard. So now I go back to the browser and go to the resource that I just talked about earlier, which is online GDB. And I just look at this code here. Okay, get rid of it. Paste in my actual program and put a breakpoint at certain places if you want to. We can put a breakpoint here and we'll debug it. Oh, by the way, we have to select the language first, so don't forget to select the language to be C. Okay, so now we can actually go ahead and debug the program. So it compiles, go into the debugger. If it complains about GDB init not found, it's okay. That is not a problem. Okay, it simply means the default instructions to execute when we first get into GDB is missing, but that's okay. It's not a problem. So what we want to do is to run all the commands in GDB. You can single step. Okay, so single step like this. Oh, okay, we have to run the program first. So R or RUN both will run the program. So we'll start the execution. It will stop at the breakpoint. So right now it's stopping at this breakpoint. And it's really nice because it shows you all the local variables. So X is a local variable. It currently has a value of 0. So now we single step. X now has a value of 8, which is fine. And then if you want to single step into this mess here, that's fine too. So we single step. We are now in the first call of f. Now in the first call of f, we want to know what the arguments are or what the parameters are. X has an argument, has a value of 2. Y has a value of 6. The difference between S and N is N will it will run the entire subroutine. It will call the subroutine without stepping in to the subroutine. In other words, single stepping will go from the caller to the callee and stop at the first line of the callee. But N will run it will call the subroutine but without stopping in the subroutine. You can look at N as stepping over. That's one of the terms that other debuggers use is N is the same as stepping over, where S or step itself is stepping into a subroutine. So you're basically selecting, are we stepping into or stepping over a subroutine call. All right, so then we single step again, and it's going to go back to the same subroutine. See, it's going back into the same subroutine, but this time X is 8 because we are now talking about the second call to F, and in the second call to F, X still has a value of 8. The stack window, which is here, that's the same thing as a BT, backtrace. So if you were to type in BT or backtrace on the console window, it will give you the same information. It will basically tell you where you are and how you got there from a chain of function calls. So that's what the stack window is showing you. Are we good so far? So the stack window is essentially the same thing as BT. It just uses a window. Well, okay, so when you read the backtrace, it is saying that we are currently on line 4 inside function f, but we got here because there was a function call on line 11 in main that is causing the current execution point to be inside function f. That's basically what these two lines are telling you in BT. Now, it can be extremely helpful when we're dealing with something that is recursive, because it will show you all the levels of recursion. All the invocations that are still active will be shown in backtrace, and it is very helpful, in terms of debugging something that is recursive. All right, so getting back to the trace here, we can see 8 is the first argument or the first parameter, and -2 is the second parameter. Kind of just like what I said when I ran through the code in my head. So when we single step, it will basically do the calculation, but it won't show you anything because we are not storing the expression into a variable, so we can't really see what value it is returning. So when we single step again, we get back into main and do the assignment. So at this point, you can either print X, or you can just go to local variables, and you can see that 8 has a value of 18 in decimal. 18 in decimal is 1/6 in hexadecimal. If you want to look at the value of X in hexadecimal, I think this will do it. There we go. So in hexadecimal, X has a value of 12, which is what we saw in GDB, because location FF on the stack in RAM also has the value of 12. So now, because I did not make a mistake fixing the program just ran fine, okay, and I did not need to use the trace analyzer to help me debug the program. So if for those of you who want to use the trace analyzer, because I think it is a really good tool to use, okay, the way to use the logic analyzer, that if you want to use the logic analyzer, okay, putting all the files into the same folder really helps. So let me illustrate what I mean by that. Okay, so I'm going to copy all the files into the temp folder. So the first one is, we have to copy the processor 0003.circ file, alu.circ, as well as regbank.circ into the same folder. And mine is located in here. So I'll copy all there'll be more circuit files than I need, but I'm just going to copy everything into here. It is not a directory. Oh, okay, I see. Because I have to specify the destination of the copy. Now this one you don't have to do, because in Windows you can just use the file manager to do all of this. So I have all the files copied over to this one single folder. I recommend that you set up everything like this prior to the final, so this way you don't have to scramble and try to get this done during the time that you really want to spend working on the problem. Okay, so these are the files that I want to put into here. So now I got all the circuit files, I got the RAM file, which is the CSV file, in the same folder. So once I have everything in here, I also want to copy the jar file into here. So the jar file is in CISP310. This is just me, okay? Obviously this part does not necessarily apply to you. So logisim310.jar is also copied. So now I got everything copied into the same folder. So once I have everything in the same folder, the command that I type in Linux should be exactly the same command that you type in Windows. It should make no differences whatsoever. So you first specify the jar file, and then you specify the processor file. Okay, processor 0003.circ. Now you want to do it at least once, just like this. Okay, press the enter key and make sure that Logisim doesn't complain that it cannot find the other two files. If Logisim complains that it cannot find the other two files, which is the ALU and the regbank file, then you help Logisim to find those two files. Don't forget to save Logisim once before you get out of the GUI mode, because this will make sure that the next time you run it on the command line, it wouldn't have a problem finding those two files. Okay, so now that I have verified that we can run it in this mode using the CLI, now we can supply the rest. Okay, we can now say tty table dash load, and then we specify the RAM file, which is sample.csv, and then we use a redirect symbol, which is the greater than symbol, to sample.tsv. Okay, and then press the enter key. Now we go back to the logic analyzer. Okay, And the logic analyzer is right here. This is just like one of those infomercials, where I have, the ovens already going, all the materials already prepped. So I just kind of pull it into here. And then we do the import, upload, and sample.tsv is the trace file. And then we specify replace current sheet, use the tab as a separator, convert, note do not convert, okay, specify no for the automatic conversion, import data, and then we go to the analysis tab. I don't think, this bar here, how fast it moves depends on your computer's processing speed, because I think all this processing is actually happening on the server that Google owns. But I could be wrong. I have been told, both ways. So I do not know exactly which way. But once again, you can just kind of scroll through the rows. This is a pretty short trace, so we only got, what, a few hundred lines. Yep, there we go. This is the last location, which should correspond to a halt instruction. And we can see that the stack pointer is balanced. Okay, it's back to 0, 0. And the value of 1, 2 in hexadecimal, which is 18 in base 10, is indeed stored to location FF on the stack, which is where local variable x of main is supposed to be at. So this is now this one, is redundant. Okay, this is a long way to verify that the program does work. But if I miss one step in the whole process and the program doesn't work, then the trace analyzer is going to be very helpful, because you don't have to keep modifying the program to find out what's wrong with it, because you can just go from the beginning. Okay, so let's just say that Richard did not mention that I need a JMPI to main. Then I will look at this code and go like, hey, it's going into function f right away. That's wrong. Okay, I haven't even set up the stack yet, for the arguments. Why are we in f? Then I'll realize that, oh, okay, that's because I forgot a JMPI to main at the very beginning. So the program just start executing function f as if it is the main subroutine. So that's why the trace analyzer is helpful, because it gives you the time to basically just gradually, slowly, look at the execution of the program. So between the trace analyzer, okay, you guys have heard about this multiple times already. So between the trace analyzer and the assemble tab of the assembler, they give you a lot of information for debugging purposes. So what I want to show you right now is how I want to set up the screen. Okay, so it's going to look really awkward, on where you can see, on the screen. Okay, but it will look a lot better when you have a larger screen at home, because I want to show you side by side. Okay, what you can do to make use of the trace analyzer in addition to the assemble window of the assembler. So the way you do it is you want to display these two side by side. Okay, certain things I can hide and not show. So this way I have a little bit more space to display what I think I really want to display. So we'll go ahead and get rid of the vertical tree tab so we can actually see the content. And on this side, we want to go to the assemble tab, which is this one. There we go. And the idea is you want to be able to look at the source code, you want to be able to look at the addresses, and you want to be able to look at how the program executes, at the same time, kind of on a side-by-side basis. So if you want to ever know, okay, why did we go from location 03 and to location 13, because the next instruction should be no more than 2 bytes away from a particular opcode, and this is like 16 bytes away. Why did we skip 16 bytes to get to location 13? So now you look up location 13 using column W, and you can see it is a JMPI instruction. Oh, okay, so we're supposed to start at the label main, but did we actually start with the label main? Okay, so we look up the label main, which is, I think I just get past it right here. So the label main is right here. It is at location 13, and that's exactly where we continue execution after 03. So we know, okay, we just confirmed that that unconditional branch happened. So this is how I imagine people would do to handle the final, is to statically go through the code, okay, catch as much as possible. It's never going to be 100%, okay? So if you are expecting to be able to catch everything, using just a static analysis, it's not going to happen. I missed a few things, okay? Richard and a few other people, helped me to spot all the problems. So even I missed a few things. So don't expect to spot everything, just statically, okay? Use the trace analyzer, okay? Run the code through and find out, what it does using the trace analyzer, and then use that to spot problems. But you still need to understand what the program is supposed to do. And to do that, okay, let me go back to Discord, make sure that people are not asking questions. So to do that, okay, you start with the C code. So it's really kind of important to look at the behavior of the C code. And GDB Online is one great resource to do this, simply because it is web-based, you don't need to install anything, and it's always there, okay? So it's a great resource. If you have your own code blocks or command line GCC and GDB, you can use that too. Okay, I don't really have any preferences myself. As long as the tool works, okay, it works as far as that is concerned. But this gives you an idea of what the C code is doing. So this way you can expect what should be happening to the variables, the parameters, and whatnot when your version of the assembly code runs. And I'm going to make the C code to be as close as possible to resemble what you can do in assembly. In other words, the type of the variables and the return values will be 8-bit, only. So that way, when you look at the outcome in C code, it'll be exactly the same as what you should expect in the assembly code. So are we doing okay? I mean, this is just kind of a quick run through of a somewhat simpler version of what you will encounter tomorrow. All right, I'm not seeing any questions. All right. So what we'll do today, okay, so I'll be online, okay, for sure, until noon or 1 o'clock, okay, so if you have any questions, I'll be answering those questions right away. I'll be kind of online, on and off, for the day, and I probably will stop answering questions by maybe 9 to 10 p.m. today. And then tomorrow I'll be up by maybe 8 o'clock, so I can answer some questions prior to the beginning of the final. So that's kind of my plan. And right now, if there are no questions, I'm going to stop the live stream, and then I'll try to think of a way so that people who want to use a different editor can still do that. All right, so I'm not seeing any questions. I'm going to stop the live stream at this point.